guys, welcome to today's grade 11 physical sciences show. I'm Katleho. Today we have a special revision lesson on Newton's laws. We have selected highlights from lessons shown earlier in the term just to help you guys revise all the work we've done together in the first term. You can download all your notes for today's show on learnextra.co.za/live. You can also post all your comments, all your queries, all your questions on our Facebook page, which you guys are familiar with by now, which is facebook.com/learnextra, as well as on our Twitter page, which is @learnextra. Guys, please, let's get on with today's lesson.
I'd like to get straight into a problem. So let's go to problem number one, question number one. And here it is. It is taken from a previous exam paper, and this is a really good hint. If you can get some old exam papers, this one was taken as far back as the year 2000, and it was a GDE exam paper. Go and practice them, go and look at them. It is before the NCS. So if you can get them, all the best to you, and make sure that you go through them. So here's this one. It's not a terribly difficult one, but we need to take note of it. It says a crate with a mass of 50 kilograms is pulled along a rough floor. So bear in mind, we must be thinking rough floor means that there's probably a force of friction by a boy exerting a force of 100 newtons. So there we've got a picture, and if they haven't given you a picture, you need to draw it. 50 kilograms, 100 Newton force. Now what do they say to you? They say you must draw a force diagram to show all the forces acting on the crate and label the forces. Okay, so let's do that. The first thing we're going to do when we do a force diagram, we're going to make sure that we indicate the object. We can draw it as a box like it is, and we're just going to add in all the diagrams. This is not a free body diagram. Of course, you could just reduce it to a dot, and I like to do that myself. So I'm going to draw a dot to represent the box, and I'm going to say what forces are acting on it. Well, from the diagram, we know that the force applied is going to be acting to the right. So we're going to say this is the force applied. That was the pull of the boy. What else do we know? From this idea here, we know that there's a frictional force, and we can put that in. If you read the full question, you'll see the next question is to calculate its acceleration. So we know that the frictional force is not going to be bigger or not going to be equal to the applied force. In this case, it's going to be smaller. The object is accelerating. What other forces do we know? Always remember that we've got a downward force, the force of the earth acting on the object, and that's equal to the mass times the acceleration due to gravity. And the last thing that we need to bear in mind is there's the force of the surface, which we're going to call the normal force. And that's pushing up. It's the force of the surface pushing up on the box. So bear those in mind. We've now labeled them. You could do it as a little key and be more explicit. And you could put this down here to say Fn is labeled. This is the normal force. And you'd put down Fg, it's the weight of the object, it's the force of the earth on the object, and the force applied. So give the full answer, particularly if they say label it. It's the pull of the boy, of the rope, or whatever it was, and then Ff is the force of friction. And there we've got it. Right, let's move on. We work with diagrams to make sure that we're getting it right so that we can do some calculations. Can we see if there's a resultant here? Well, I've already mentioned it to you. Bear in mind, that the normal force is the same magnitude as the force of the earth pulling it down. So the only two forces that are really acting is this one, and they're not equal. So we know that there is a resultant. The resultant will be equal to the force of friction plus the force applied. But before I go and do that calculation, I need to make sure that I understand that there's direction to it, that the force of friction is in the opposite direction to the force applied. So let me write this down and say, for direction, I'm going to say that something that goes to the right is positive. And I'm going to use that sign notation, which means that the force of friction, which acts to the left, has a negative sign in front of it. But let's move on. The next question tells us, calculate the magnitude of the frictional force caused by the floor if the acceleration of the crate is 1,5 meters per second. So there was something different. If we read it, we would have seen that in the calculation. But we've got some important information that we've read off our diagram, and let's make sure that we've got it now. We know from the diagram that the resultant force is equal to the force applied plus the force of friction. And over here, what we're going to say is the force applied, if we look back, was 100 newtons, and we say that's in the positive direction, so it's that. How are we going to find? We need to find, look from the question, we need to find this. So how are we going to find the resultant? Well, we know that they're related to each other, but we also know that the resultant force by Newton's second law is equal to the mass times the acceleration. And they've given us, look, they've been very nice. They've been giving us the acceleration. The important thing here to recognize is that we recognize that this is the direction of acceleration, and this is the same direction of the resultant force, because the force applied is going to be bigger than the frictional force. The frictional force is just going to be a little force that's holding it back a little bit. Okay, so let's do the calculation now, and let's work out what the frictional force is. So we're going to say this is mass times acceleration. This is 100 newtons. This one we don't know. We know that it's going to have a negative answer because it's in the opposite direction. So let's substitute in. We substitute in the values for mass. It was 50 kilograms times the acceleration of 1,5 meters per second is equal to 100 plus the force of friction. Now, remember, we're not able to work out what this is. And these are added as vectors, but we'll come to that and we'll see exactly what's happening. 50 times 1,5. Let's do the calculator, even though we can do it in our heads. It's not difficult to do in our heads, but let's use the calculator. 50 times 1,5 equals 75. So we now know that the resultant force, look at this, the resultant force is 75. We know that the applied force is 100. Now guys, this doesn't take rocket science to work out what the frictional force is. What must I add to 100 to get 75? I hope you can see that we've got to add minus 25, because minus 25 plus 100 is going to give you 75. You can, of course, work it out and rearrange the subject of the formula, and you will get something like this. You will get 75 minus 100, and you can check that that equals minus 25 newtons. Now, you can't leave your answer like that. You can't leave it like that. You've got to say that is equal to 25 newtons opposing the motion, opposite to the motion, Or you can even say 25 to the left. It's better to say opposite, but because we might not have this exact diagram, You might have had to draw the diagram. So I prefer to say in the opposite direction to the motion. It just means it's more general and it's safer to put as the answer. Now, I hope you've got those points. Be very careful as you're going through these type of questions.
Now it's time for a break, so don't go away and we'll be right back. Welcome back, Mindsetters. Today we are doing revision. Even though we are selecting highlights from previous shows, you can still follow me on Twitter @LearnExtra or post or comment on our Facebook page, facebook.com/LearnExtra. Right now, let's do some more revision.
Let's get to it, and it's one that is often has come up in the past when this sort of thing was done previously and examined previously. This comes from the November paper that was written in the Northern Cape, 2000, and it was a high-grade question. So we can go and have a look at it. It says, 2 blocks of 3 kilograms each are connected by a rope. There they are. There's the 3 kilogram blocks. They're placed on a frictionless horizontal table. A third block of 4 kilograms, there's the third block, is connected to the others by a light rope over a frictionless pulley. So that's frictionless, as shown in the sketch. So all of that is there. What we need to recognize is that they mark the blocks X, Y, and Z as well. And the first thing they ask us is to calculate the acceleration of the 3 kilogram block marked X. So how are we going to do this? We recognize, first of all, when you get a problem like this, please draw a diagram or take note of the diagram so that you can see what all the forces are that are acting on this object. Now, we're only interested for the block X in the horizontal forces. Yes, I know that there is a force downwards and there's the normal force that acts opposite, but those aren't going to help us accelerate. The thing that we need to remember is that there is no friction. And if there is no friction, that means that the only force that's acting on this block is in fact a force in that little rope that's going to pull it in that direction. So how are we going to work out the acceleration? We're going to say the acceleration is equal to the resultant force divided by the mass. And if we got that, then we're safe. We're altogether okay. So the resultant force on this block, we don't know yet. So we're going to need to just leave it like that for the moment. And we're going to say, what do we know about the resultant force? Well, the resultant force, we just simply rearrange, is equal to the mass 3 times A. And that's all we can say for the moment on that particular block. Let's move to the second part of the question. And the second part of the question says, hold on, guys. We don't just want to know about block A. We want to know what is the tension between X and Y. What is this force over here? Now, let's try and work that out. We haven't answered fully that top question. And I want to get to showing you how to do it by looking at the next question. I just want to get the third part of the question out, was to calculate the resultant on the 3 kilogram block marked Y. And then the last part of this question, that was the last part. So we've got to put these questions together and try and work them out. So 3 kilogram block marked X, we only know at the moment the resultant force. So there are different ways of doing it, and I'm going to make sure that we look at it separately. The first statement that I've got is about block X, and I'm going to say the resultant force on block X is equal to 3 times its mass. Now, what about Y? What about this block? What's happening on Y? Now, what we can say is on Y, look at it, we've got Y over here, we've got a pull that way and a pull that way. So this is the force of between x, y, and this is the force that I'm just going to say is a force applied. So what we recognize is that there are two forces here. The resultant of those two is going to, that's going to be the resultant. We're going to have to add the one to the other, and we're going to have to get them sorted out. This is the tension in the rope. This is the tension in the rope. And so we're going to say the resultant of this one is going to be, let's keep the force to the right positive, and we're going to say it's T minus Fxy. That's the resultant, and we know that's equal to 3 times, the mass was 3, sorry, the acceleration, I've done something wrong here. That should have been A, 3 times A, because they were both 3 kilograms. They're both 3 kilograms. This one's 3 kilograms, that one's 3 kilograms, and we're wanting to get the acceleration. So it's a bit of a long way around, but we're almost there. The final thing that we're going to do is we're going to say Z. This is this bit here. Now, look at what Z is doing. Z has got the force of gravity acting on it, and it's got this tension that was in the string. And the tension here at this end and the tension there is the same. So I'm going to write up a little equation and set it up. And I'm going to say what I need to know is that the force downwards, the Fg, is greater than the tension because it's moving down, minus tension is equal to 4 times the acceleration. The 4 comes from the mass. And so I've got 3 equations, and I'm going to need to solve these simultaneously. And that's the trick here. You've got to add these together and put them into an order. And that's exactly what I'm going to do. So I'm going to say to myself, I've got the tension between Fx and xy as 3a, and I know that that one there. So I'm going to just substitute that in to this equation. So I'm going to get T minus 3a is equal to 3a, and then I'm going to take this equation here of Fg, which I'm going to write as mg, Fg being mg because it was the mass times the acceleration. So let's just substitute that in very quickly. Fg is equal to mg, which is 4 times 9,8. I need to work that out. So quickly, let's get the calculator and let's get it onto the screen. And we're going to say 4 times 9,8 equals, there's my answer, 39,2. So 4 times 9,8, 39,2. Please remember that, Atik. Don't forget it, 39,2. So the value is 39,2. So if I substitute that in, I can now get some detail going here. I can say 39,2, almost done, 39,2 minus t is equal to 4a. Now, I hope you can see something. There's something interesting happening. I've got 2 equations. If I add them together, look what happens. If I add these 2 equations together, I'm going to get t plus minus t. Those are going to cancel out. So that cancels with that. And then I'm going to get 39,2 minus 3a is equal to 7a on this side. And that just simply means that I can expand it and get 39,2 is equal to 10a. Brilliant. So what am I going to say? A is equal to 3,92 meters per second per second. I've got it. I've worked out the acceleration, and that's a critical point. Notice I've used simultaneous equations to do that. I've looked at each of the aspects of the system, and they're not all acting in the same direction, but I've combined them, and I've worked out the acceleration. Atik, are we okay?
Yes, definitely.
Okay, let's move on. The next part of the question now becomes really easy because I can take either of these 2 equations, okay, and I can use them to work out. If I know the acceleration, I can work out what's happening in the second part, and that's exactly what I'm going to do. So we want the tension between the ropes. I now know what the acceleration of x is. I know that if you go back there, I worked out that the acceleration, remember, was 3,92. So if I want the tension in the rope, I only have to look at one end. And I can say the tension is equal to the resultant force on x, which was the mass times the acceleration. We know what the mass was. The mass is 3 kilograms. The acceleration was 3,92. And we can therefore work out that the tension is equal to we divided that by 10 to get the acceleration. We're going to multiply that by 3, and we get the answer that the tension is 11,76. 11,76 newtons, and that would be the tension in that rope, and in this case, it is acting to the right. It's the rope pulling on X. Okay. What I'd like you to do is to have a look and see if you can work out that the tension is the same at the other end. It really is. Believe me, you can substitute in and you'll find it is the same. Now, if I know that that's the tension, the last part of the question was what's the resultant force on the 3 kilogram block? Now, let's look at this way. The resultant force is equal to the mass times the acceleration. We know that the tension is in that direction. There's another force in that direction, and we can work out what the resultant force is on the 3 kilogram block marked Y by simply putting in 3 times A and working it out. It's not that difficult. If they really wanted to make it tricky, what they would have done is said to you, what's this tension? Then you'd have to use that and work out to find what that tension is. Guys, these problems take practice. Don't give up. Don't think that because you've seen it and, I don't know what's going on, that you need to give up. Don't. Persevere. Practice. Look at the solutions. They are on the notes as well.
Okay, guys, I hope you're really, really enjoying this revision session. If you are struggling and need help, remember to post on the page or send an email to helpdesk@learnextra.co.za. Now it's time for a break, so don't go away. We'll be right back. Welcome back, guys. I hope you are getting into the idea of revision. Please let us know how you are doing. I'd love to chat to you guys either on the page or on Twitter. Enough of the chat. Let's get back to our revision now.
So, we start with the most basic concept, which is all objects are attracted to the earth, irrespective of their shape, size, or mass. You all know, okay, if I have to, and I'll catch it though, when I have my pen and I drop it, it drops, okay? It doesn't miraculously hang in the air, and it doesn't miraculously go up all by itself. You know it's going to fall. If I throw it up, which I won't do either because the person who looks after the TVs will hurt me, okay, and I don't want to do that because he's a big man. But if I have to throw it up, the pen will go up for a little bit, and then eventually it falls down. We all know that, okay? And if your name's Tracy, you know you fall down quite often as well because I'm quite a klutz. Mm-hmm. So, you know, I fall off stairs, and we all know we fall. It's one of those things. We understand that.
Yeah.
But what does that mean? That means there is a force of attraction between the earth, okay? So that's where we're starting with. Starting point is the earth and any object. But there's an important factor that there isn't just an attraction between the earth and any object, but actually there is a force of attraction between any objects. It doesn't matter. It doesn't have to be between the earth and the object. That's there. We experience that force of attraction because the earth is so big. Okay, so the force that the earth pulls on us is really big. So we experience it more. But even that annoying boy in the class who sits next to you, who, when you sit in your science lesson, instead of listening to a teacher, all you're thinking is, I just want to slap him, which you can't do. There's actually a force of attraction between you two as well. And now I can just hear lots of screams at home going, no. And you know what, even worse, there is actually a force of attraction between you and your books. Granted, it's very small.
It's very important.
Very important.
Very important.
Anyway, it's very small, but there is a force of attraction. Okay? That force of attraction is very, very important. That can be described to us in Newton's law of universal gravitation. This is a definition, grade 11s. You must learn it. And Newton's law of universal gravitation says to us, the force of attraction, first part, not the force of attraction. Force is a vector. That means I have to give direction. Attraction is direction, okay? So the force of attraction between two objects, and this is between any two objects in the universe, which theoretically means there is a force of attraction between you and the moon. But remember, the moon is so far away from us right now that really that force of attraction becomes so small it doesn't play a role in our lives, okay? And that force is directly proportional. Remember, directly proportional means that if the force increases, something else increases. And what is that something else? It's the product of their masses. So now you're saying, hang on, wait, Tracy, at the beginning of the lesson, you said you were going to prove to us that the force of gravitational acceleration is independent of mass. But now you're telling us we need to put mass in. You need to hang fire for that one. But it's directly proportional to the product of their masses. Product means multiplication. And inversely proportional. Inversely proportional means if one thing goes up, the other goes down. Okay? To the square, you square it, of the distance between their centers. That last part of the statement is very important, grade 11s. Often, when we see this, we get the first part right, and then we get this inversely proportional to the square of the distance between them. We can't do just the distance between them. When we're considering something like the force between myself and the Earth, you've got to remember the Earth is ginormous. So we take it from the center of gravity, okay? But because here, with Newton's law of universal gravitation, we're really dealing with it on a very big macroscopic level. So we're dealing with big objects. It's still valid on a microscopic level. So this plays a little bit of a role in terms of bonding and intermolecular forces, but they're such small masses that we don't often consider it as being that important. But in terms of big objects, very, 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 very important. You take it from their center, okay? Which then means when you're looking at questions, be careful, because often questions that involve the Earth, they'll tell you that something gets moved to, say, 2 radiuses above the Earth, and then we forget about the radius of the Earth in the first place. When it's between people, take the distance between them, and we're fine. Okay, so what does this look like as an equation? And this is, here it is. Ooh, extend my page. Force of attraction F is equal to G, new G, it's not acceleration due to gravity, times mass 1, mass 2, divided by r squared. So F is force, and force is measured in newtons, okay? This is always force of attraction, never, ever, 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 ever going to be repulsion. So we don't need to worry about that. G is a very important constant, okay? G is known as the universal gravitational constant. Okay? Why is it universal? Because as far as we know, You never know. Once we start exploring space and start living on other planets, maybe we'll find it's not true anymore. This is valid anywhere in the universe, okay? It is a constant. That means it has a value. Lucky for you, the value is given on your information sheet. I'm hoping it's not too new for a lot of you, but it's equal to 6,67 times 10 to the minus 11 newtons per kilogram squared. I think I got those the wrong way around. Let me just check. Yes, that's what I thought. Okay, let's just quickly do this. It's newtons. No, that one. Meters squared per kilogram to the minus 2. The meter squared and the kilogram to the minus 2 gets cancelled out as we go along, so it actually is the one that gives us the newtons, all right? Where does this come from? Lots and lots and lots and lots of experimentation, okay? Lots of experimentation. And in fact, I just wanted to show you something. And I have to thank John for this, but Bill Bryson, he's one of those wonderful writers who writes all sorts of things, and he wrote a book called A Short History of Nearly Everything. Okay, it's one of those books where you read it and then forget everything, but he's just amazing at what he wrote. And basically he's looking at the history of the world and scientific experiments and thoughts and things that have changed. And of course everyone wanted to prove Newton's laws, and comes to Newton's law of universal gravitation. And then along came some, I think they might have been Spanish, I can never tell, I'm really bad with names, so I'm going to butcher some names right now. And these scientists came along, and it says here, they worked for a decade, 10 years, on trying to work something out, and then somebody else beat them to it.
Whoa. That's
just got to be upsetting. That would do it for me, but moving on. Anyway, now, what Newton conjectured, in other words, what he said could happen, and these guys actually set out to prove it, was this. He said in his books that if a plumb line, which is just a line that we hang similar to a pendulum that tells us whether something's straight, and they conjectured that if it was hung near a mountain, okay, that it would incline. In other words, it would bend slightly towards the mountain. Mountain's got a big mass, okay, and it's affected by the mountain's gravitational mass as well as the Earth's. That's just freaky if you think about it, okay? So, if they measured, and they said if you measured the deflection accurately and worked out the mass of the mountain, you could calculate the universal gravitational constant. That is phenomenal. That just actually blows my mind, okay? They did this all over the world, by the way, and they went around the world trying to find great mountains to do it with, because they also realized the shape of the mountain, whether it was regular or square or that sort of thing. They even came down to South Africa to use Table Mountain for a while, just to see, because we know we love our square mountain, okay? But they realized somebody else beat them to the answer on that one. That's a bit scary. That would just kill me. Anyway, moving on. So, not only did Newton prove this through experimentation and extremely complicated maths for his time, it's been proven in the last couple of in the last century, which is amazing for me. M stands for mass. Mass must be measured in kilograms, and R is the distance between their centers, which means it's got to be in meters. So how do we use this? Let's quickly tackle a question, and then we'll take a break. Very typical type question that you could get. Says to us, calculate the magnitude, size, okay, of the force between a box of mass 100 kilograms. So let's write that in as mass 1, okay, and a person, let's make that mass 2, of 75 kilograms if they are 0.5 meters apart. Grade 11s, you have to make the assumption that because they didn't say between their centers, that's what they mean. Okay, don't get all picky about this and go, I can't answer the question because I don't know if it's between the centers. Just make that assumption. The only time it becomes incredibly critical that it's between their centers is really when we're looking at planets and big objects. This, we assume it's between their centers, okay? What is that? This is actually not bad because now we have to calculate the force. So all we need to do is substituted in. Okay, now I'm going to do it underneath. I would do it next to it on a page, but it's just that gravitational constant's so big. So, F, don't forget to put your equation, mass 1, mass 2, r squared, okay? Gravitational constant, 6,67 times 10 to the minus 11. Mass 1 was 100. Mass 2 was 75. And it was 0.5 meters squared. Calculator work, so important. Let's just see what this would look like on the calculator, okay? So we're going to go, and it's in maths display. I'm going to show you some stuff. 6.67. We use the exponent button to the minus 11. We're going to times by 100, times by 75. Now, I know some of you might have been taught to use brackets and stuff. I prefer to do it this way because I know you guys get confused where all the brackets should go. So now we go equals. So that's my top line answer. Don't write it in. Now we're going to divide that answer by 0.5 and square it. Oh boy. If we look at that answer, it's got millions of noughts. Please, you don't have to write it. I would prefer you to write it in scientific notation. So make sure you can change your calculator. So watch, I'm going to do it for you. We're going to go Shift, Setup, Mode 7 on this calculator, and I'm going to go to 3. Can you see it already in scientific notation for me, which is brilliant. So this is 2,00 times 10 to the minus 6 newtons. That is so tiny. Not a chance I'm going to feel that. Now what we're going to do is we're going to do some problems. Now I've taken them. The nice thing is this has been in the curriculum for hundreds of years, just about. That's what it feels like. So if you can actually get hold of old question papers from 10, 12 years ago, nice Newton laws questions, nice Newton's laws of gravitation questions, such a good place to find practice questions, okay? So I've actually taken the question papers from 2001 and 1999. Okay, some of you hopefully were born then if you were in grade 12, if you're in grade 11 already. And what we're going to do is I'm going to show you how to do a couple of questions which we call proportion questions. And these ones can, and ratio questions, these ones can get a little hairy. So I do it in a slightly different way because we need to make sure that you get the marks for a question like this. Often they're multiple choice and they start to do all sorts of weird and wonderful things and you look at them and you go, but there are no numbers. That's okay. Let's look at the first question. It says, the distance between two similar mass pieces, so they're saying to us right at the beginning, is that the masses are the same, or thereabouts, is r. So the distance is r, and the magnitude of the force they exert on each other is F. I'm going to do this in arrows. So in other words, their force between them is F, is G, mass 1, mass 2, over r squared. Now, I don't know mass 1 and I don't know mass 2, but that doesn't matter. We're going to see now what they're wanting. And I'm going to change pen so it's a little bit easier. If the distance, so if r is halved, so they're saying to me I'm now going to use half of r, and the mass of both objects, both of their masses, is also halved. So in other words, I have 0.5 of the first mass and I have 0.5 of the second mass. What is the magnitude of the force they now exert on each other? They want this in terms of the original force. So what they're asking you is, by half in the distance and their masses, what have we doubled the force? Have we tripled the force? Have we halved the force? What have we done? How does the force change? This is where we've got to be careful. Your teachers, and there's nothing wrong with it, perfectly fine, might teach you to do this with a proportion, okay? Go, well, force is directly proportional to mass. It can just get a little complicated. So what I want to show you is a little bit of a trick where you look for something you know. That's my trick. So watch what we're going to do. My new force is G, okay, times my new mass, which is half of the original one, times my other new mass, divided by my new distance squared. Stay with me. Now we go, okay, let's put all the constants, the numbers, together. So we're going to go, so we're going to put all the variables on one side of the fraction. We're going to put all the constants together. So we're going to go, okay, this is 0.5 times 0.5, which is 0.25. Because remember, this is multiplication. It can be in any order. It doesn't make a difference. G, M1, M2. Now, it's 0.5 r squared, so 0.5 is also squared, and 0.5 squared is 0.25 r squared. Now we work out what the numbers would give us if we just had them, and this one's actually quite nice because we've got 0.5 divided by 0.25 divided by 0.25, which is 1. Okay, so we have 1 times G M1 M2 over r squared. Now I'm hoping someone is looking at this going, oh wait, Tracy, I see it. Actually, maybe I do want to move this aside. Watch here. Doesn't G1, and isn't that G M1 M2 over r squared what I've got over here? So doesn't that mean that actually the force is the same? That my new force, because I've got this, ooh, sorry, board doesn't like 2 instructions at once. I have that being the same over there. Look for something we know. So in other words, my new force is equal to my old force. So by halving the masses and halving the distance, we actually cancelled out the differences. Okay? Stay with me. Let's do one more. That's like this one. This, they love these ones. Love them. Because now it gets a little bit less, how does that work? Watch here. They say to us, a large planet. You know, they're just trying to make it sound exciting. A large planet has a radius 10 times that of the Earth. Radius is 10 times the Earth's. So the radius of my planet is 10 times the radius of the Earth, which I'm going to call RE so I can remember it. It has a mass 300 times that of the Earth. So my planet's mass is 300 times the mass of the Earth. And it's round about here that we start to go, but Tracy, I don't know the radius of the Earth, and I don't know the mass of the Earth. It's okay. They don't expect you to know them. If you are expected to use the actual values in a calculation, either you are going to have to work one of them out, and they'll give you the other, or they will give them to you. Don't worry about it, okay? Because I'm going to show you. I'm going to do the same things we did in the last question. However, if the weight of the body is 500 newtons on the Earth, okay? If G is 500 newtons on the Earth, what is his weight on the planet? In other words, they're saying to you, if the force of attraction between the body and the Earth is 500, he now goes to another planet, which is 10 times the radius, 3 times the mass. What is his weight going to be there? Not quite, the numbers aren't quite as nice as the last one, because they're not going to cancel each other out, but we're going to do it step by step. The 500 newtons is the force of attraction between the Earth and the person. So we're going to do this. So that's the force of the Earth, and it's G, the mass of the object, which we're not going to worry about, the mass of the Earth divided by the radius of the Earth squared. We're all okay with that. Let's deal with the planet. I'm going to do it in another color so you can see what I'm doing. So the force that he's going to experience on the new planet is G, mass of the planet divided by the radius squared, because I called it big R. But that's not going to really help us. So we want to get it in terms of mass of the Earth, radius of the Earth, okay? So we go over here and we say, fine, we knew that this was G, the mass of the man and the object didn't change, because that's constant, much to some of our horror, okay? It is constant. The planet was 300 times the mass of the Earth and 10 times the radius of the Earth. So I've substituted the mass of the planet, radius of the planet with values. I'm going to do the same thing I did last time. I'm going to take the value, the numbers to the front. So I've got 300 times G, mass of the Earth. 10 squared is 100. Sorry, wrong R. So this is 100 times RE squared. Now watch here. This is the same as that. It's the same value. That, from the Earth, is 500 newtons. They told us the mass, the weight on the planet was 500 newtons. So now we go, oh wait, they're the same. We know the value of that set. So what we can do here is we can go, okay, fine. 300 divided by 100 is, hopefully you're screaming at the TV now going 3. Of course it's 3. This whole part that I've circled is worth, well, it has a value of 500. So now we have 3 times 500, which is 1,500 newtons. So even though he's going to a planet which is ridiculously big compared to Earth, 300 times the mass, 10 times the radius, his weight will only be 3 times bigger. Okay? What you also need to recognize is radius makes a huge difference here. Okay? It's very, very important about the radius because we square it. So small changes in distance make a big change in force. What am I telling you need to do here, grade 11s, okay, is with ones where they change things and they go 3 times this, 2 times that, half this, quarter that, all of those sort of things, it becomes a little bit of an English nightmare, I understand that. Find something you know. You are always going to have something you can compare it to. That's the important thing here. Find something to compare it to.
Guys, we've come to the end of today's show. Thank you for joining us and chatting to me on our Facebook page. Remember, you can visit our website at any time that you want to get the notes as well as watch the videos. The website is www.learnextra.co.za/live. And if you're stuck, remember you can send an email to helpdesk@learnextra.co.za and tell us where exactly you're stuck so that we can help you. Don't forget to look out for more news on Library Month on our Facebook page as well as on our website. And remember, you can also join us for Easter Revision. Bye, guys.
Of the rope or whatever it was, and then FF is the force of friction. And there we've got it. Right, let's move on. We work with diagrams to make sure that we're getting it right so that we can do some calculations. Can we see if there's a resultant here? Well, I've already mentioned it to you. Bear in mind that the normal force is the same magnitude as the force of the Earth pulling it down. So the only 2 forces that are really acting is this one, and they're not equal. So we know that there is a resultant. The resultant will be equal to the force of friction plus the force applied. But before I go and do that calculation, I need to make sure that I understand that there's direction to it, that the force of friction is in the opposite direction to the force applied. So let me write this down and say, for direction, I'm going to say that
Hello Hello guys, welcome to today's grade 11 physical sciences show. I'm Katleho. Today we have a special revision lesson on Newton's laws. We have selected highlights from lessons shown earlier in the term just to help you guys revise all the work we've done together in the first term. You can download all your notes for today's show on learnextra.co.za/live. You can also post all your comments, all your queries, all your questions on our Facebook page, which you guys are familiar with by now, which is facebook.com/learnextra, as well as on our Twitter page, which is @learnextra. Guys, please, let's get on with today's lesson.
I'd like to get straight into a problem. So label the forces. Okay, so let's do that. The first thing we're going to do, when we do a force diagram, we're going to make sure that we indicate the object. We can draw it as a box, like it is, and we're just going to add in all the diagrams. This is not a free body diagram. Of course, you could just reduce it to a dot, and I like to do that myself. So I'm going to draw a dot to represent the box, and I'm going to say what forces are acting on it. Well, from the diagram, we know that the force applied is going to be acting to the right. So we're going to say this is the force applied. That was the pull of the boy. What else do we know? From this idea here, we know that there's a frictional force, and we can put that in. If you read the full question, you'll see the next question is to calculate its acceleration. So we know that the frictional force is not going to be bigger or not. Let's go to problem number one, question number one. And here it is. It is taken from a previous exam paper, and this is a really good hint. If you can get some old exam papers, this one was taken as far back as the year 2000, and it was a GDE exam paper. Go and practice them. Go and look at them. It is before the NCS. So if you can get them, all the best to you, and make sure that you go through them. So here's this one. It's not a terribly difficult one, but we need to take note of it. It says a crate with a mass of 50 kilograms is pulled along a rough floor. So bear in mind, we must be thinking rough floor means that there's probably a force of friction by a boy exerting a force of 100 newtons. So there we've got a picture, and if they haven't given you a picture, you need to draw it. 50 kilograms, 100 newton force. Now what do they say to you? They say you must draw a force diagram to show all the forces acting on the crate, and going to be equal to the applied force. In this case, it's going to be smaller. The object is accelerating. What other forces do we know? Always remember that we've got a downward force, the force of the earth acting on the object, and that's equal to the mass times the acceleration due to gravity. And the last thing that we need to bear in mind is there's the force of the surface, which we're going to call the normal force, and that's pushing up. It's the force of the surface pushing up on the box. So bear those in mind. We've now labeled them. You could do it as a little key and be more explicit, and you could put this down here to say Fn is labeled. This is the normal force. And you'd put down Fg. It's the weight of the object. It's the force of the earth on the object, and the force applied. So give the full answer, particularly if they say label it. It's the pull of the boy,